welcome to this problem walkthrough. Today, we'll dive into LeetCode problem number 275, H-index 2. This problem is a great exercise in understanding the concept of H-index, often used in academic citation metrics, and implementing efficient algorithms to solve it. Let's get started. The H-index is a widely used metric that quantifies both the productivity and citation impact of a researcher. It is defined as the maximum value of H such that the researcher has at least H papers with H or more citations each, while the rest of the papers have no more than H citations. In this problem, you are provided with an array called citations, where each element represents the number of citations a researcher's specific paper has received. This array is guaranteed to be sorted in non-decreasing order, meaning the values are arranged in ascending order. Your task is to calculate the H-index for the researcher, but the key requirement is that the solution must have a time complexity of O log n, which suggests that an efficient algorithm, likely involving binary search, is necessary to solve the problem effectively. To determine the output, we need to find the H-index, which is the maximum value of H that satisfies the H-index condition. Let's look at an example. For the input array citations equals 0, 1, 3, 5, 6, we can calculate the H-index as follows. The researcher has 5 papers, and the citations for these papers are listed in ascending order as 0, 1, 3, 5, 6. To satisfy the H-index condition, we need to find the largest H such that at least H papers have H or more citations each. Here, 3 papers have at least 3 citations, they are 3, 5, 6. This makes the H-index equal to 3. Additionally, in the same example, the other 2 papers, which are 0, 1, each have no more than 3 citations. This matches the H-index definition, confirming that the H-index is indeed 3. Now, let's consider another example. Suppose the input array is citations equals 0, 2, 4, 6, 8. In this case, there are 5 papers, and the citation counts are 0, 2, 4, 6, 8. To calculate the H-index, we observe that 4 papers have at least 4 citations each, they are 4, 6, 8. The remaining paper, 0, has no more than 4 citations. This means the H-index for this case is 4. Now, let's analyze one more example. If the input array is citations equals 0, 1, 2, 3, 4, the researcher has 5 papers, and their citation counts are 0, 1, 2, 3, 4. To find the H-index, we need to determine the maximum H such that at least H papers have H or more citations. Here, 2 papers, namely 2, 3, 4, have at least 2 citations each, while the remaining 3 papers, 0, 1, have no more than 2 citations. Thus, the H-index for this case is 2. The problem also specifies certain constraints. The length of the array, n, can be as large as 100,000, and the citation counts for each paper can range from 0 to 10,000. Additionally, the array will always be sorted in non-decreasing order, which ensures that we can leverage efficient algorithms to compute the H-index. When solving this problem, we must also account for edge cases to ensure our solution is robust. For instance, if all citations are 0, such as citations equals 0, 0, 0, 0, the output will be 0 because no paper has any citations. If all citations are the same, such as citations equals 5, 5, 5, 5, the H-index will be the number of papers, which is 4 in this case, because all 4 papers have at least 4 citations each. For a single paper, such as citations equals 1, the H-index is 1 because the single paper has at least 1 citation. Lastly, for large input sizes, such as an array ranging from 0 to 10,000, the algorithm's efficiency becomes crucial, and the required O log n complexity ensures that even large datasets can be handled effectively. To begin with, the brute force approach calculates the H-index by directly iterating through all possible values of H, from 0 to the total number of papers. For each potential H value, we count how many papers in the citations array have at least H citations. If this count is equal to or greater than H, we update the H-index. While this method systematically checks every possibility and is straightforward to implement, it is computationally expensive. Specifically, for each H value, the algorithm traverses the entire array, leading to a time complexity of O n squared. Despite using no extra space, this approach quickly becomes inefficient as the number of papers increases, making it unsuitable for larger inputs. Now, recognizing the inefficiency of the brute force method, we turn to an optimized approach that leverages the sorted nature of the input array. By using binary search, we can significantly reduce the time complexity. The key insight is that for any index in the sorted citations array, the number of papers with at least as many citations as the value at that index can be calculated as n minus the index. This observation allows us to check whether a given index satisfies the h-index condition without needing a full linear scan. With two pointers initialized at the start and end of the array, we use binary search to find the optimal h-index. Depending on whether the condition is met at the midpoint, we adjust the pointers to continue searching either to the left or the right, narrowing down the range efficiently. In terms of complexity, this binary search approach is highly efficient. It reduces the time complexity to O log n, since it repeatedly halves the search space until the condition is met or the range is exhausted. Additionally, it operates in constant space, requiring no extra memory. What makes this method particularly advantageous is its ability to fully exploit the sorted property of the input array, turning what would otherwise be a tedious and time-intensive task into one that is both quick and scalable. Compared to the brute force method, this approach is a significant improvement, especially when dealing with large datasets, making it a much more practical solution. Given these considerations, the optimized binary search approach is the clear choice for solving this problem. It takes full advantage of the sorted nature of the citations array, achieving a time complexity of O log n that makes it highly efficient. While the brute force method is conceptually simpler and easier to implement, its quadratic time complexity makes it impractical for large datasets. The critical breakthrough was realizing that the sorted order of the array allows us to calculate the number of papers meeting the h-index condition in constant time at each step of the binary search. This insight enabled us to replace a linear scan with a far more efficient process. While the binary search approach requires a slightly deeper understanding, it strikes a perfect balance between simplicity and performance, making it the optimal solution for this problem. The h-index is a metric used to measure a researcher's productivity and the impact of their publications. It is defined as the largest value of h such that the researcher has at least h papers with h or more citations each. To calculate the h-index, we need to consider an array called citations where each element represents the number of citations a paper has received. The goal is to determine the maximum h that satisfies the condition. There are at least h papers with h or more citations, and the remaining papers have fewer than h citations. For example, if the input array is 3, 0, 6, 1, 5, 3 papers have at least 3 citations each, making the h-index equal to 3. We also need to account for constraints such as handling 0 citations or cases where the h-index is 0. This sets the stage for solving the problem efficiently. One way to solve this problem is through a brute force approach. The idea here is to iterate over all possible values of h, from 0 to n, where n is the number of papers. For each h, we count how many papers have citations greater than or equal to h. If this count satisfies the h-index condition, we update the result. To implement this, we initialize h_index to 0 and use nested loops. The outer loop iterates over potential h values, and the inner loop counts the number of papers with sufficient citations. If the count meets or exceeds h, we update the h-index. This approach ensures correctness by checking every possible value for h, but it involves a nested iteration, which can be computationally expensive. After completing the nested iterations, the final value of h_index is returned as the result. While the brute force method is straightforward, it is not the most efficient solution due to its n² time complexity. To address this, we can consider an optimized approach that leverages sorting to simplify the calculation. By reordering the data, we can eliminate the need for nested loops and determine the h-index in a single pass over the sorted array. In the optimized approach, we first sort the citations array in descending order. For example, if the input is 3, 0, 6, 1, 5, the sorted array becomes 6, 5, 3, 1, 0. Next, we iterate through the sorted array while checking the condition, citations I greater than or equal to I+1, where I represents the current index. If the condition holds, we update h_index to I+1. The iteration stops as soon as the condition fails. This method ensures that we only perform a single pass through the array after sorting, significantly reducing the computational complexity compared to the brute force approach. The sorted array reveals the relationship between the number of papers and their citation counts directly, making it easier to calculate the h-index efficiently. To compare the two approaches, the brute force method has a time complexity of O(n) squared due to its nested loops, while the optimized approach has a time complexity of O(n log n) because of the sorting step. Both methods have a space complexity of O(1) since they do not require additional data structures. The optimized approach is particularly efficient for larger datasets, as sorting allows us to directly observe the relationship between the number of papers and their citations. Edge cases also need to be carefully handled, such as when all citations are 0, when all papers have the same number of citations, or when there are no papers at all. These scenarios ensure that our implementation is robust and accounts for all possible inputs. Sorting plays a crucial role in simplifying the problem by arranging the citations in descending order. This reordering allows us to perform a linear pass through the data, checking the h-index condition at each step. By stopping the iteration early when the condition fails, we avoid unnecessary computations. The critical condition citations, I greater than or equal to I+1, ensures that both the number of papers and their citations meet the h-index definition. Additionally, handling edge cases explicitly, such as an empty array or all zeros, ensures that the algorithm does not encounter runtime errors. These optimizations collectively make the sorting-based approach more efficient and practical for real-world use cases. For example, consider the input citations equals 3, 0, 6, 1, 5. After sorting, we get 6, 5, 3, 1, 0. As we iterate through the array, at index 0, citations 0 equals 6 satisfies 6 greater than or equal to 1, so we update h_index equals 1. At index 1, citations 1 equals 5 satisfies 5 greater than or equal to 2, so h_index equals 2. At index 2, citations 2 equals 3 satisfies 3 greater than or equal to 3, so h_index equals 3. At index 3, citations 3 equals 1 fails 1 4, so we stop. The final h-index is 3. In terms of complexity, the sorting-based approach has a time complexity of O(n log n) and a space complexity of O(1). It is the preferred method for moderate to large input sizes due to its efficiency. Always consider edge cases to ensure the implementation is robust and handles all possible inputs correctly. This implementation solves the h-index 2 problem using a binary search approach, which is efficient given the sorted nature of the input array citations. Here's a detailed breakdown. 1. Initialization. The length of the citations array is stored in n. 2 pointers, left and right, are initialized to the start and end indices of the array respectively. 2. Binary search loop. The algorithm enters a loop that continues as long as left is less than or equal to right. This ensures we explore all potential candidates for the h-index. 3. Midpoint calculation. At each iteration, the midpoint index mid is calculated. This divides the search space into 2 halves. 4. Comparison. If citations mid equals n mid, it means that there are exactly n mid papers with at least n mid citations. This satisfies the definition of the h-index, so we return n mid. If citations mid is less than n mid, it implies that the current h-index candidate is too low, and we need to search in the right half of the array. Thus, left is updated to mid plus 1. Otherwise, if citations mid is greater than n mid, the current h-index candidate is too high, so we search in the left half by updating right to mid 1. 5. Final return. If the loop exits without finding an exact match, the value n left is returned. This represents the maximum h-index possible given the remaining search space. #efficiency. This solution has a time complexity of O log n due to the binary search, making it highly efficient for large datasets. The space complexity is O(1) as it uses a constant amount of extra space. ### edge cases. If the citations array is empty, n is 0, and the function correctly returns 0. If all elements are 0, the h-index is also 0. If the array has very high citation counts, the algorithm adjusts accordingly to find the correct h-index. This concise and efficient implementation leverages the sorted nature of the input to provide an optimal solution to the problem. This is the Java implementation of LeetCode problem number 275, h-index 2. It mirrors the logic from the given Python implementation. The binary search algorithm is used to efficiently calculate the h-index for a sorted citations array. Key differences include type declarations for variables, Java's explicit array handling, and the use of the int data type for indexes and calculations. This implementation is concise, leveraging Java's idiomatic constructs while preserving the core logic of the Python solution. In this first example, we are given the sorted array of citations 0, 1, 3, 5, 6, and need to determine the h-index. The h-index is defined as the maximum value h such that the researcher has at least h papers with h or more citations each. To solve this, we use a binary search approach. We start by initializing n as 5, which is the length of the citations array, and setting left to 0 and right to 4, the indices of the array. In the first iteration, we calculate the midpoint mid as 0 plus 4, // 2 equals 2. At this index, citations, mid, is 3, and end mid is also 3. Since these two values are equal, we have found our h-index. Therefore, the output for this example is h equals 3. Now, in the second example, the citations array is 0, 2, 4, 5, 6. Again, we initialize n as 5, left as 0, and right as 4. For the first iteration, we compute the midpoint mid as 0 plus 4, // 2 equals 2. At this index, citations, mid, is 4, and end mid is 3. Since citations, mid, is greater than end mid, we adjust our search range by setting right to mid 1, which makes right equals 1. In the second iteration, we calculate mid as 0 plus 1, // 2 equals 0. At this index, citations, mid, is 0, and end mid is 5. Since citations, mid, is less than end mid, we move left to mid plus 1, making left equals 1. For the third iteration, with left equals 1 and right equals 1, we calculate mid as 1 plus 1, // 2 equals 1. Here, citations, mid, is 2, and end mid is 4. Since citations, mid, is still less than end mid, we update left to mid plus 1, resulting in left equals 2. At this point, the binary search terminates because left is now greater than right. The h-index is then calculated as n left, which is 5, 2 equals 3. Therefore, the output for this example is also h equals 3. Moving on to the third example, the citations array is 0, 0, 0, 0, 1, representing a case where the researcher has very few citations. We initialize n as 5, left as 0, and right as 4. In the first iteration for this example, we calculate mid as 0 plus 4, // 2 equals 2. At this index, citations, mid, is 0, and end mid is 3. Since citations, mid, is less than end mid, we update left to mid plus 1, which makes left equals 3. In the second iteration, with left equals 3 and right equals 4, we calculate mid as 3 plus 4, // 2 equals 3. Here, citations, mid, is 0, and end mid is 2. Again, since citations, mid, is less than end mid, we set left to mid plus 1, resulting in left equals 4. In the third iteration, mid is 4 plus 4, // 2 equals 4, where citations, mid, is 1, and end mid is also 1. Since these values are equal, we have found the h-index, which is h equals 1. Thus, the output for this example is 1. The time complexity of this algorithm is primarily determined by the binary search process. In a binary search, we repeatedly divide the range of indices in half until we isolate the target index. For an array of size n, this halving occurs approximately log_2, n, times, meaning the binary search itself runs in O, log, n, time. Within each of these iterations, we perform constant time operations like calculating the middle index, comparing values, and updating pointers. These operations are simple and do not depend on the input size, so they contribute O1 time per iteration. As the binary search dominates the runtime, the overall time complexity of the algorithm is O log n. The space complexity of the algorithm is straightforward because it uses a constant amount of additional memory. The input array citations is passed directly into the function without requiring extra storage. Additionally, the algorithm uses a few integer variables, such as n, left, right, and mid, which occupy a fixed amount of memory regardless of the size of the input. Since there are no recursive calls or dynamic memory allocations, the algorithm does not incur additional stack or heap usage. As a result, the overall space complexity is O(1), meaning it requires a constant amount of space. When comparing the binary search approach to the brute force approach, we can see a significant improvement in time complexity. The brute force approach involves scanning the entire array linearly and checking conditions for each element, resulting in a time complexity of O(n). However, the binary search method leverages the sorted nature of the array to eliminate half of the search space in each iteration, reducing the time complexity to O log n. Importantly, both approaches share the same space complexity of O(1), as neither requires additional memory. This makes the binary search a more efficient solution overall while maintaining minimal memory usage. Now, let's analyze the algorithm's performance across different scenarios. In the best case, the target condition citations, mid, = n mid is satisfied on the first iteration, which results in a time complexity of O(1). On average, the binary search performs log_2 n iterations as it narrows down the search space, leading to an average case time complexity of O log n. In the worst case, the target is not found, and the algorithm exhausts all possible indices before returning the result based on the final left pointer. Even in this scenario, the time complexity remains O log n. Therefore, the algorithm is consistently efficient across all cases. To mathematically validate the time complexity, consider that the binary search reduces the search space by half in each iteration. Starting with n elements, the number of iterations required to narrow down to a single element is log_2 n. Each iteration performs constant time operations like arithmetic and comparisons. Combining these, the total time complexity is the product of O log n iterations and O(1) per iteration, which simplifies to O log n. In summary, this algorithm improves the time complexity from O(n) in the naive approach to O log n, while maintaining an O(1) space complexity, making it a highly optimized solution for the problem. One common mistake when solving the H-index problem is misunderstanding its definition. Many people incorrectly assume that the H-index is simply the maximum citation count of a single paper. However, the H-index is actually the largest number, H, such that there are at least H papers with H or more citations. Misinterpreting this can lead to faulty logic when iterating or counting citations, resulting in incorrect outcomes. Another mistake is failing to handle edge cases, such as when the array of citations is empty, all values are 0, or all citations are extremely large. These scenarios can lead to index out-of-bounds errors or inaccurate results if not accounted for. Finally, some solutions mistakenly assume that the citations array is always sorted, which is not guaranteed unless explicitly stated. Sorting an unsorted array unnecessarily increases complexity, making your solution less efficient. Another issue to avoid is relying on inefficient brute force methods. Using a nested loop to count citations for each potential H value results in O(n²) time complexity. This approach is impractical for large inputs and will likely fail time limits in competitive coding platforms. Logical errors, such as off-by-one mistakes in indexing or boundary conditions, are also common. These can occur when iterating through the array or comparing citation counts and can completely disrupt the computation of the H-index, particularly in edge cases. It's essential to approach your implementation with attention to detail to avoid these pitfalls. When discussing the H-index in an interview setting, it's helpful to understand its real-world application. The H-index is widely used in academia to measure a researcher's productivity and the impact of their work. Sharing this context during your explanation can show a deeper understanding of the problem. Focus on optimizing your solution, especially if the interviewer encourages efficiency improvements. For instance, you could explore sorting-based approaches with O(n) log n complexity or counting sort methods with O(n) complexity. Clearly explaining the trade-offs between time and space complexities in your approach is also important. For example, sorting simplifies implementation but may not be optimal for very large datasets. Be sure to address edge cases upfront, such as empty arrays or unusual citation distributions, to show thoroughness. Lastly, be adaptable, as interviewers might introduce variations, such as handling sorted inputs, dynamic updates, or even fractional H-index calculations. Demonstrating flexibility in your approach is key. There are a few related problems that share similarities with the H-index concept. For example, H-index 2 on LeetCode, where the input array is sorted, requires a binary search approach. Problems like top k frequent elements and kth largest element in an array also involve counting and prioritization techniques, while sort characters by frequency emphasizes ordering based on frequencies. In terms of alternative approaches, a straightforward method is sorting the array in descending order and iterating to find the H-index. This approach is simple but has n log n complexity, which may not scale well for large datasets. A more optimal solution is to use counting sort, where you build a frequency array and iterate from the highest value downward to calculate the H-index in n time. For sorted input, binary search is particularly efficient, allowing you to determine the H-index in log n time. The two-pointer method is another useful approach, particularly for variations that involve handling sorted data or scenarios with dynamic updates to the input. While this method can be highly effective, it often requires more intricate implementation details, so careful attention is needed when designing and coding the solution. This technique is especially relevant when you need to efficiently manage constraints related to sorted arrays or adjust dynamically to changes in citation counts. Great work! To summarize, we tackled the H-index problem using an efficient binary search approach, which is ideal for sorted arrays. Remember, mastering binary search can significantly improve your problem-solving skills. Thanks for tuning in, and don't forget to like and subscribe for more content. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!